From the grand cosmos to the smallest particles, our universe is governed by a set of rules. For millennia, humanity has sought to understand these rules, to write them down in the universal language of mathematics. Today, we'll explore the 9 most important equations that have shaped our world. We'll journey from the foundations of geometry, to the laws that govern the stars, the arrow of time, the secrets of the atom, and the very fabric of our digital age. This is The Mechanist, and these are the equations that built our modern world. As we prepare to unlock the code of our universe together, consider subscribing to The Mechanist to join every new exploration into the wonders of science and engineering. If you believe that mathematics is the language of the universe, show it with a like. And let us know in the comments which of these titans of thought you believe had the single greatest impact. Our journey begins in ancient Greece, with an equation so fundamental that it's often the first piece of real math we learn in school, Pythagorean theorem: the sum of the squares of the legs is equal to the square of the hypotenuse. Attributed to the Greek philosopher Pythagoras, this elegant formula describes a simple but profound relationship in any right-angled triangle. It states that the square of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the other 2 sides. But its importance goes far beyond the classroom. This theorem is the bedrock of geometry and trigonometry. It's used every single day in construction, to ensure that corners are perfectly square. It's essential for navigation, allowing sailors and pilots to calculate the shortest distance between 2 points. Even the GPS in your phone uses this ancient principle to pinpoint your location. It's a timeless piece of mathematical beauty that connects abstract thought to the physical world. For centuries, humanity looked to the heavens and saw chaos. The movement of the planets was a mystery. Then, in 1687, Isaac Newton published his magnum opus, Philosophiae Naturalis Principia Mathematica, and with it, an equation that brought order to the cosmos: the law of universal gravitation. This equation describes the force of gravity between 2 objects. It tells us that this force, F, is proportional to the product of their masses, m1 and m2, and inversely proportional to the square of the distance, r, between their centers. The g is the gravitational constant, a number that scales the force. Suddenly, the same force that makes an apple fall from a tree was the same force that keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. It was a revolutionary idea, that the laws of physics are universal. This equation laid the foundation for classical mechanics and allowed us to predict the motion of celestial bodies with incredible accuracy. Newton didn't stop there. His second law is one of the most famous in all of science. It tells us that force equals mass times acceleration. This may sound simple, but it's the cornerstone of classical mechanics. It explains how objects move and why they stop. It allows us to predict motion, to simulate reality, to design everything from bicycles to rockets. In a crash test, engineers use to calculate impact forces. In a rocket launch, this equation determines how much thrust is needed to overcome gravity. Whether it's designing a roller coaster or testing a robotic arm, this law is always in play. It's not just theory, it's motion, measured and mastered. Our next equation deals with something more abstract but just as fundamental: energy, chaos, and the arrow of time. It's the core idea of the second law of thermodynamics, often expressed as the change in entropy is always greater than or equal to 0. This states that in an isolated system, the total entropy, S, or disorder, will always increase or stay the same over time. Think of it this way: your coffee will always get cold. A broken egg will never spontaneously reassemble itself. An ice cube in a warm room will always melt. This is entropy in action, the natural tendency of things to move from order to disorder. This law explains why perpetual motion machines are impossible, why energy transfer is never 100% efficient, and it gives us a direction for time itself. The universe, as a whole, is moving towards a state of maximum entropy. It's a profound and somewhat sobering concept that underpins everything from chemistry to cosmology. From heat to electrons, Ohm's law governs the flow of electricity. Voltage equals resistance times current. That's the basic principle behind every circuit, every power source, every electrical system. Whether you're charging your phone or powering a city, Ohm's law is involved. It helps engineers design safe, efficient systems that deliver power where it's needed. In modern electronics, from computers to EVs, controlling current is essential. And it all comes back to this simple, powerful equation. Our next set of equations laid the groundwork for our entire modern technological world. They aren't just one, but 4 coupled equations known as Maxwell's equations. Developed by James Clerk Maxwell in the 1860s, these equations unified electricity, magnetism, and light into a single, comprehensive theory of electromagnetism. In essence, they describe how electric charges create electric fields, how moving charges, currents, and changing electric fields create magnetic fields, and how changing magnetic fields create electric fields. One of the most stunning predictions of these equations was that these interacting fields would travel through space as a wave, an electromagnetic wave, and that the speed of this wave would be the speed of light. This revealed that light itself is an electromagnetic wave. This discovery directly led to the invention of radio, television, radar, Wi-Fi, and every other form of wireless communication we use today. Every time you send a text, watch TV, or use your GPS, you are using technology built upon the foundation of Maxwell's elegant unification. At the dawn of the 20th century, our understanding of space and time was about to be shattered. A young patent clerk named Albert Einstein proposed an idea that would change physics forever, encapsulated in one of the most famous equations in history: energy is equal to mass multiplied by the speed of light, c squared. This is the mass-energy equivalence from his theory of special relativity. It reveals something astonishing: mass and energy are two sides of the same coin. E is energy, m is mass, and c is the speed of light in a vacuum, a colossal number. Because c is squared, this equation tells us that a tiny amount of mass can be converted into an immense amount of energy. This is the principle behind nuclear power, which generates electricity by splitting atoms. It's also the source of the devastating power of atomic bombs. More than that, it redefined our understanding of the very fabric of reality, proving that mass is a form of concentrated energy. It's the equation that unlocked the power of the atom. At the quantum level, things get strange. And Erwin Schrödinger gave us a way to understand that strangeness. His equation describes how quantum particles behave, not with certainty, but with probability. This isn't just for physicists. Without quantum mechanics, we wouldn't have semiconductors, lasers, or MRI machines. Schrödinger's equation is the heartbeat of quantum theory, and the reason your phone, your internet, and your digital life exist. Finally, we have the Navier-Stokes equations, the crown jewels of fluid dynamics. These equations describe how fluids move, whether it's air in the sky, water in a pipe, or blood in your veins. They're essential in meteorology, aerospace, medicine, and oceanography. They model hurricanes, design jet engines, and simulate airflow over a Formula One car. And yet, they're so complex that we still don't fully understand them. Solving them in general is one of the great unsolved problems in mathematics. Maybe I should make a video explaining these problems. From triangles to turbulence, these equations are more than just symbols. They are the language of the universe. They allow us to build, to explore, to discover. Which equation impressed you the most? Let me know in the comments. If you enjoyed this video, give it a like to support the channel. Subscribe and turn on notifications so you don't miss the next deep dive into the machines and math that shape our world. And if you want to see how these equations are used in real engineering, hit subscribe, because this is The Mechanist, and we turn theory into reality.